The Ladybird browser team just accomplished something that should have taken months. They rewrote their entire JavaScript engine from C++ to Rust in 2 weeks using AI coding assistants, generating 25,000 lines of code with 0 regressions across more than 65,000 tests. This wasn't supposed to be possible. Just 2 years ago, Ladybird's creators explicitly rejected Rust, arguing that its ownership model was incompatible with their object-oriented C++ architecture. They even explored Swift as an alternative before abandoning it due to poor C++ interoperability and limited platform support. But the promise of memory safety eventually won out. Memory safety bugs account for roughly 70% of security vulnerabilities in system software. Both Firefox and Chromium have already begun integrating Rust components into their codebases, recognizing that C++ simply can't eliminate these risks at scale. The Ladybird team chose their JavaScript engine called lib.js as the test case for AI-assisted translation. This was strategic. The engine consists of well-defined self-contained components, a lexer, parser, abstract syntax tree, and bytecode generator. More importantly, it has extensive test coverage with over 52,000 Test 262 compatibility tests and 12,000 Ladybird-specific regression tests. The translation process relied heavily on Claude and Codex, but this wasn't just feeding code to an AI and hoping for the best. The team used hundreds of small targeted prompts with constant human oversight. They would translate individual functions or small modules, then immediately run the test suite to catch any behavioral changes. The most remarkable aspect was their approach to ensuring identical behavior. Rather than writing idiomatic Rust code, they deliberately mimicked the original C++ patterns. The Rust version maintains the same register allocation strategies, the same memory layout decisions, even the same algorithmic choices that might not be optimal in Rust. This produced bytecode that was literally byte for byte identical to the original C++ implementation. When you compile the same JavaScript code with both versions of the engine, the output is mathematically identical. That level of fidelity is unprecedented for a language port of this complexity. The team even used adversarial review processes, having different AI models critique and verify each other's translations. This caught edge cases and subtle bugs that might have been missed with a single model approach. But the technical achievement raises important questions about code quality and maintainability. The resulting Rust code intentionally violates many Rust idioms. It doesn't leverage the language's powerful type system or ownership model effectively. It's essentially C++ semantics expressed in Rust syntax. Some developers argue this defeats the purpose of using Rust in the first place. If you're not writing idiomatic Rust, are you really getting the benefits of memory safety and performance that the language promises? The Ladybird team acknowledges this is a first pass, with plans to gradually refactor toward more idiomatic Rust patterns. The broader implications extend far beyond browser development. This demonstrates that AI can now handle production-critical code migrations with perfect behavioral fidelity. That's a significant milestone for the software industry, where legacy codebases often represent millions of dollars in accumulated business logic. Consider the typical enterprise scenario. A company has a critical C++ service that's been running for years, accumulating features and edge case handling. The cost and risk of a manual rewrite has kept them locked into C++ despite known memory safety issues. AI-assisted translation could change that calculus entirely. The timing is significant too. Ladybird joining Firefox and Chromium in adopting Rust signals broader industry momentum toward memory-safe systems programming. When independent browser projects start making the same architectural decisions as the major players, it suggests the transition is becoming inevitable rather than optional. There are still limitations to consider. The Ladybird approach worked because they had comprehensive test coverage and well-defined module boundaries. Many legacy codebases lack both. The JavaScript engine also has relatively clean interfaces compared to something like a graphics rendering pipeline or network stack. The economic implications could be substantial. If AI can reliably translate systems code while maintaining perfect behavioral compatibility, it dramatically reduces the cost of technical debt remediation. Companies could migrate critical infrastructure to memory-safe languages without the traditional risks of introducing regressions. Looking ahead, the success of this approach will likely accelerate similar efforts across the industry. Expect to see more experimental AI-assisted translations of critical systems components, particularly in security-sensitive domains, where memory safety bugs have real-world consequences. The Ladybird project has essentially provided a proof of concept that large-scale, production-critical code translation is now feasible with current AI capabilities. Whether other projects can replicate this success will depend heavily on their existing test coverage and architectural boundaries, but the precedent has been set.